What are you doing, Mr. Newton?
What am I doing? What's level 5's in? Like every day, level 5's.
Right, so let's have a look at this example. So, since the start of the academic year, Mr. Newton has kicked off on 8 separate days. He's given level 5 detentions on 63 days of the 90 in school, and he's kicked off and given level 5 detention on 5 separate days. So let's draw ourselves a Venn diagram showing all this information. So remember to draw the box. We've got 2 circles in this case, and we've got K for kicking off and L for level 5. So let's go to the middle. That's where we should always start. So he's kicked off and given level 5 detentions on 5 separate days, so 5 in the middle. We know that he's kicked off on 8 separate days, so we've already got 5, so that's another 3 where he only kicked off, and level 5 detentions, he's done that in 63 of the 90 days. We've already got 5 in the middle, so that leaves 58. So if we add all these up, that comes to 66, but we know that we're looking out of 90 days. So 90 take away 66 leaves 24. Right, so what are we actually asked then? So it says, what is the probability that given he is kicked off, he gives a level 5 detention in the same day? So we're not looking out of 90, we're restricting ourselves to just looking at this circle. So that means that our probability is only going to be out of 8. Okay, because we're only looking in this circle. And we're looking for what's the probability he gives a level 5 detention in the same day. Well, out of this circle, 5 of them are days where he gave level 5 detentions, and so that is 5 out of 8. Now, so there's our answer, but we could have used slightly more sophisticated notation. And so the way we could write what is the probability that he's kicked off, given that he's kicked off, he gives a level 5 detention, we could write that like this. We could write the probability that given he is kicked off, so we already know he is kicked off, what is the probability he gives a level 5 detention? So that's what this notation means. Given that he's kicked off, he gives a level 5 detention. Now what did we do to work this out? Well, what we did was we restricted to looking at this circle. Well, that's the probability of K, or out of the probability of K. And we wanted that he'd done both. So that's the probability of giving a level 5 detention and kicking off. Okay? So that is, we're restricting our probabilities to looking out of that, and we just want this bit. So we can actually give this formula in general. So in general, we have, if we want to find the probability of A, given that B has happened, then we restrict ourselves to looking at just out of stuff where B has happened, and we're looking for where both things have happened. So probability of A intersection B. Right, well, we can actually rearrange this as well to give something called the multiplication rule. And so all we need to do is multiply both sides by the probability of B, and so we'll get the probability of A intersection B is equal to the probability of B times the probability of A given B. This is called the multiplication rule.
Okay, in this first example, we're given these two events, C and D, and we know the probability of C is 0.2, the probability that D occurs is 0.6, and it tells us here that the probability that C occurs, given that D has already occurred, is 0.3. Alright, the first thing it asks us to find is the probability of D occurring given that C has already occurred. So sort of flipping around this one that they've given us here. Now I'm going to do this using the multiplication rule twice, because what I really want to know is the probability of C and D occurring, because then I can use that to find the probability of D occurring given C is occurring. And I can work this out because I know that this equals, from the multiplication rule, the probability of C given D times by the probability of D occurring. And we've got all of that information. That equals 0.3 times by 0.6, which gives me 0.18. So now I know the probability of C and D. I can go back to my original question in part A, the probability of D given that C has occurred. Well, I know, using the multiplication rule again, that that's the probability of D and C divided by the probability of C. And really, the probability of C and D and the probability of D and C both occur, and this means they both occur at the same time, this means they both occur at the same time, they're the same thing. So this equals 0.18 divided by, and the probability of C is 0.2, so that gives me my answer of 0.9. So if C occurs, it's very, very likely that D will also occur. Right, for part B, I'm going to draw my Venn diagram to help me. So if I draw it in this space here, I've got my event C, I've got my event D, draw a little sample space. I know that the probability of C and D is 0.18, so I can work out from that, well, the probability of C is 0.2, so 0.2 take away the 0.18 already accounted for is 0.02, and similarly with D, the difference between 0.6 in the question and the 0.18 leaves me a probability of 0.42 here of just D and not C. Right, adding that up, I've got 0.02 plus 0.18 is 0.2, plus the 0.42 is 0.62, so 0.62 there leaves me 0.38 outside. And that's kind of handy because we can see for part B, it asks us the probability of C complement, so that's C not occurring, and D complement, and D not occurring. So if neither of them are occurring, well, anywhere in these circles, one of at least C or D is occurring, and in this little middle bit, both of them are. So the only place that neither C or D are occurring is this bit outside around the edge. So it's this bit here, this 0.38. So I know that this is equal to probability of C complement and D complement, neither of them occurring, is 0.38. And then for the final part, this is the one where we've got to be really careful. C complement, C not occurring and D occurring, well, I would say let's use our hatching. So I want C not occurring, that's happening anywhere outside of this C circle, so I'm going to be careful not to go into the C circle, and I'm going to start coming down this way to avoid hitting the edge of the page. So I'm going down, skipping over the C circle, all the way down, and D occurring, whoops, typo there, and D occurring, so just to be clear, probably says C not occurring and D occurring. So I'm going to hatch everywhere that D occurs because I want probability C not occurring and D occurring. So D occurs here, inside this circle. So where does it overlap? Well, the crisscross is in this bit out here. So the probability, oh no, that's D complement. The probability of C complement, no typo after all, and D occurring is equal to this bit here where C doesn't occur but D does, 0.42. Alright, so that is example 1, take 1. Okay, for this next example we've got two events, let A and B be events such that the probability of A is 3/10, the probability of B is 2/5, and the probability of B or A equals 1/2. And the first thing it wants us to find out is this probability of B occurring given that A has occurred. Now I hope by now you're screaming, use the multiplication rule. But we need to know a crucial piece of information first. First, to do that, I'm going to need to know the probability of B and A occurring to work that out. Now in the other example, we did the multiplication rule twice because we had the information for that. This time I've got to go a slightly different route. I hope you can spot, I've got the probability of A, I've got the probability of B, I've got the probability of B or A occurring. So to find this probability of B and A occurring, well actually here, I'm going to use the addition rule that we looked at last week first. So the probability of B and A occurring is going to equal the probability of B plus the probability of A occurring minus the probability of B or A occurring. And we've got all that information, that equals 2/5 plus 3/10 minus 1/2, and I'm sure we all know that that is equal therefore to 1/5. Alright, so the probability of B and A both occurring is 1/5. I can now plug this value straight into my multiplication rule to work out what the question actually asks me, the probability of B given A. So I know from the multiplication rule that that's the probability of B and A divided by the probability of A. So that's going to be equal to, I'm going to draw my fraction line, the probability of B and A is 1/5 divided by 3/10, and that's just equal to 1/5 divided by 3/10. I'm sure you're all screaming at the screen, 2/3. Well done if you spotted that. So that's my part A done. For my part B, well, in this case I'm going to draw my Venn diagram again. I think if in doubt, sketch it out. So to draw my Venn diagram, I've got my event A, I've got my event B. I can work from the middle outwards. I know the probability of B and A, put that in the middle, that's 1/5. I know the probability of B is 2/5, so 2/5 take away the fifth already there, leaves me a fifth over here. I know the probability of A is 3/10. 3/10 take away the fifth that's already there, well that's the same as 2/10. So 3/10 take 2/10 leaves me 1/10. If I was to add all that up, that's the equivalent of 2/10 plus 2/10 plus 1/10, that's 5/10 or 1/2. So that leaves me 1/2 outside. Now for part B, we'll do this down here. It asks me for the probability of B occurring given that A has not occurred. Given that A has not occurred. Alright? So I know that A has not occurred. So I'm going to get rid of all the space that A has not occurred. I want all the space that A has not occurred. So using our hatching, this is all the space where A has not occurred. This is A complement. So all of these places A has not occurred. Where has B occurred given that A has not occurred? Well, it's this part here. Alright? In here. But it's not out of everything. We know that the probability that A has not occurred, so we want the probability of B and A complement divided by the probability of probability of A not occurring, A complement. So that's how it would work in the multiplication rule. Well, we want B and not A, so that's going to give me a fifth. That's a fifth. That's B and not A is a fifth from my diagram, divided by the probability of not A. Well, that's just going to be 7/10. We can see up here the probability of A complement is going to be equal to 1 minus the 3/10. It's going to be 7/10. So, tenths. So my answer is going to be 1/5 divided by 7/10. That's going to be 2/7. So that's the probability of B occurring given that A has not occurred. Just the probability of B and not A. Well, we get that from the diagram, 1/5 divided by the probability of not A. Well, that's 1 minus the probability of A. There you have your answer.
You can also show the box plot.
What?
I've messed it up.
What have you missed out, Doug?
I think who does not like and does not like dogs. I think it's meant to say cats there.
Oh yeah.
I don't know what this is all about either. Who?
Who?
Oops. On all over the whole sheet.
What, you put M there?
Yes.
You put M there?
Doc, you also put M there,
Put
M
that.
there.
It shouldn't be Q1.
Aren't we looking for the first quartile here?
Doug? Okay, so we've got to look at this question here, and we're going to draw a tree diagram to represent all the information. Okay. So we've got a normal school day. The probability of Dr. will make a mistake with mathematical working is 0.05, quite low. Given that he's not making a flip learning video on that same day. Okay. Notice that language given. Probability of Dr. making a video flip learning on day is 0.2. Okay, so I want to start here because the given stuff usually happens afterwards. So the video comes first. So I'm going to use a bit of notation here. For video, I'm going to say V for video. I'm using V complement or not V, not video. So the chance it's going to make a video is 0.2. And I'll put that on the branch of the tree diagram. And then the probability of not making a video must be the complement of that, 0.8, adds up to 1. Okay, so once it's made a video, we're looking at the chance of making a mistake. So this first bit of information, if he's not made a video on the same day. So this is this section down here. So if he's not made a video, we've got two options. He's going to make a mistake, M for mistake, or M complement, not M, not a mistake. And that value, make a mistake, 0.05, very low as we said. Okay. So that means this, got to add up to 1, so we're going to have 0.95 as the complement. Okay then. Well, let's have a look at this top branch then. So he's made the video, and he either makes a mistake or he does not. Okay, well this information is here. If he is making a video, the probability of him making a mistake is 0.4. So video, makes mistake is 0.4. Okay, we can notice the given language popping up here. So this will be 0.6, complement of that. Now I'm just going to put on some of the actual notation what these probabilities are. So this is the probability of B making video, the probability of not making video. Okay, well this probability is, given he's made a video, he's made a mistake. So the probability that he makes a mistake, given the video, and that notation we've got for given, that line. And this is the probability that he doesn't make a mistake, given he's made a video. Okay, and we can have a look here. This is the probability that he makes a mistake given that he's not made a video. And we can fill in the last one. He's not made a mistake given he's not made a video. I expect that to be quite good. Okay. Right, the result of these is quite interesting. So here we've got the probability that he's made a video and then he's made a mistake. So notice the notation we're using there. It's the probability he's made a video and not made a mistake. Probability not made a video and made a mistake. Probability he's not made a video and he's not made a mistake. Okay. Now you'll probably remember from GCSE that about times and on the branches get the probabilities, and we can see that this obeys one of our multiplication rules that we've mentioned earlier on in the video. So I'll just write it down here for the top line. Probability of B times the probability of M given B. That gives me the probability of B and M. Now you can see that's just the same as what we've seen before, with a couple of the letters swapped around. We had probably this version of it, with B's and A's in. Now, notice that I've got B is A and the M is B. So you can see that that's applying. So the question we've looked at is on your note sheet is, what's the chance he's made a video and then he's not made a mistake? So let's look on these branches. Made a video, not made a mistake. We've got 0.2 times 0.6 is 0.12. And we can go through and fill these in. I think we're assuming that if he makes a video, it looks like he's under more pressure, so he's making more mistakes. So his probability of making a mistake is higher. Okay. Right, so there may be some dependence here, and we can look at that if we want to later on. Okay, so that's how to set up a tree diagram from the information like that.
Okay, so this is another one of those examples where we've got two ambiguous events, events A and events B, but we know that the probability of event A given that B has occurred is 0.1, the probability of event A occurring given that B has not occurred is 0.6, and the probability of B occurring is 0.3. Now, there's more than one way you can tackle this, as I'm going to show you, but screaming out to me straight away, I can see that I can draw a tree diagram. If I've got the probability of B here is 0.3, I know therefore straight away that the probability of B complement, probability B doesn't happen, is 1 minus that, 0.7. So I can draw my tree diagram. I've got 0.3, that's the probability of B. I've got therefore 0.7 is the probability of B complement. So here B's happened, and given that B has happened, I know the probability of A happening is 0.1. So the probability of A given B. So therefore, the probability of A not happening given B's happened must be 0.9. Alright, down here B's not happened, and I know that the probability of A given B doesn't happen is 0.6. So let's draw it like that. That's A, and therefore the probability that A does not happen, A complement given B does not happen, B complement, get that 0.6 nice and clear, must be 0.4. So before I even worry about the questions, I can quickly work out, well, 0.3 times 0.1, this probability is 0.03, 0.3 times 0.9, this probability is 0.27, 0.7 times 0.6, this probability is 0.42, and 0.7 times 0.4, this probability is 0.28. And really, the maths is easy, multiply along the branch. It's just about understanding your diagram to answer these questions. After this, it's fairly straightforward, because I can say, well, in question A, it says the probability of A and B occurring. Well, where on my diagram does that happen? Well, 0.3 times 0.1, B occurs here, A occurs here, A and B is just here, so this is my answer to part A. It must be 0.03. For B, in a similar fashion, it says the probability of A occurring and B not occurring. Well, B doesn't occur down here, and out of these two options, this is where A does occur, so this must be my answer to part B, 0.42. In C, this is the first time really, if you understand your diagram, C is the first time you've got to stop and actually think. It asks me for the probability of A, given the information we've got. Well, I know that that must be the probability of A and B happening plus the probability of A and B not happening. Because A can happen with B, A can happen without B. There's no other way that A can happen. So therefore, if we add these together, we've got the probability that A happens, independently of anything else. So, looking at this, where does that occur? Well, here A happens with B, so this is one part of my C. And here A happens without B. So we've already found the two answers, we're just going to add them together. 0.42 plus 0.03 gives me 0.45. Alright, those are my two scenarios from the tree where A can happen. So that's the probability of A. Now we've got the probability in part D, where it asks us to find the probability of B occurring given that A has occurred. Well, if we think about this using our multiplication rule, this is the probability of B and A occurring divided by the probability of A. Now, in our diagram, we've shrunk it down to here. We know that A has occurred, so this is our only two options. This plus this must be our denominator, which we've already worked out in C. That's the probability of A. So I know that this equals something over 0.45. And what's that something? Well, probability of B and A occurring. That was this top branch. So that's 0.03. And that equals 0.06 recurring. If I do the maths right there, 0.06 recurring. So that's the probability of B occurring given that A has occurred. Very similarly, in part E, it asks us the probability of B occurring given that A has not occurred, given A complement. And in a similar way on the multiplication rule, well, that would be the probability of B and A complement, so B occurring and A not occurring, divided by the probability of A complement. Now we don't know A complement, but it is not difficult to work out. We've got two ways of working it out. Way number one, this is where A complement happens. So similarly to part C, we could just add those two values up. Or we can just say if the probability of A happening is 0.45, the probability of A not happening is 1 minus that. Either way, you would get the probability of A complement to be 0.55. Whether you added those two values or whether you did 1 minus 0.45, you'd get the probability of 0.55. So that's probability of A not happening. The probability of B happening and A not happening, where does that happen? B happening is up here, A not happening is there. So it's this one here. This is what we want for part E's numerator. So that is going to be 0.27. And if we do that sum, that gives me a value of 0.490 recurring. So that's 0.4909999 and so on. Alright, so that's how you do it with a tree diagram. but it's not the only way you can do it. We could also have taken the Venn diagram approach. Now, to show you how this one would have worked, well, straight away I can say, if I want to know in A, the probability of A and B happening, well, using my multiplication rule, that's the probability of A given B times the probability of B. This is all information we have. So that's equal to 0.1 times 0.3, which, as we've already seen, is 0.03. I can again use the multiplication rule for B. It wants the probability of A and B complement, B not happening. Well, we already saw how probability of B complement is 0.7. So that's similarly, we've got this here, 0.6. We've got the 0.7 here. So just in the same way, that's A given B not happening times probability of B not happening. So that equals 0.6 times 0.7, and that gives me 0.42. Simple as that. Now I have enough information to be thinking about drawing that Venn diagram. So I've got my probability of, I've got my event A, I've got my event B, and I know the probability of A and B is 0.03. I know the probability of A and not B is 0.42. And to fill in this space here, I can just do the difference between 0.03 and 0.3. So that's 0.27. Alright. And then if we want to know what's out here, we just do 0.45, 0.65, 0.65 plus 7 is 0.72. So this would be 0.28. This would be 0.28 out here. Right. Now I want to do part C. So it says probability of A. Well, clearly we can see this circle is A, so it's 0.42. Add 0.03. So that's 0.45 again, isn't that lucky? For part D, it says the probability of B given that A has occurred. Well, if I know A has occurred, I'm looking at this circle here. A has definitely occurred, that's my denominator. So again, that's 0.45, those two values added. And I want B to occur, well that happens here in the 0.03. So 0.03 divided by that, again, gives us 0.06 recurring. For part E, again, we just saw this with the tree diagram. How am I going to do this with the Venn diagram? Well, it asks me for the probability of B occurring given A does not occur. Well, that's going to equal, let's see, A does not occur. Using my hatching, I can see A doesn't occur. All of this area here. That's 0.27 add 0.28. So that's my 0.55. And the probability that B does occur
Right, okay then. So, say I've got two events, A and B. Right. Well, say out of these two events, B happens. Okay. What's going to happen to the probability of A? Is that B's happened first going to alter what's happened to A? Well, we've talked about this. This is actually the probability of A given B. Okay. But say this probability of A could go up. So B happens, for some reason the probability of A increases. Okay. Or it could decrease, or up or down. It kind of depends on what happens to B. Oh, right, okay, so A depends on B. Oh, right, okay. No, I want to start again. Okay. Okay, so we've got two events, A and B. Now imagine one of them happens. Say B happens. Does the probability of A change? Okay. Does the probability of A depend upon B? Okay. So B could happen, the probability of A could go up. The probability of A could go down. Or it could stay the same. Okay. Well, we've been talking about this probability of A. It's probability of A given that B's happened. Probability of A given B. Right, well, if it's gone up, I sometimes call that like a positive dependence. A depends on B, B's happened, probability of A's increased. Okay, cool. Or it could go down. What about if it stayed the same? So, probability of A is exactly the same, even though B's happened. So the probability of A given B hasn't changed. Probability of A, it's the same thing. Oh, this means A and B are completely independent. B hasn't affected A at all. Okay, so these are independent. Okay, so we've got independent events. Probability of A is equal to the probability of A given B. Okay. Well, this has a few ramifications. I think we've just seen a multiplication rule. There's a probability of A given B times the probability of B was the probability of A and B, or A intersection B. Well, if probability of A and B is probability of A, because these things are independent, then we've got the probability of A times the probability of B equals probability of A and B. So you need to make a note that if you've got independent events, that means that probability of A is the same as probability of A given B, because B hasn't changed it, and you can use this rule here. This is really important in some examples. Okay. Well, the other thing that can happen here is if, so this is when it stayed the same. We saw about when it went up, we don't really look at that so much. But if it's gone down, say it's gone down so far, the probability of A is 0, okay? So B's happened, and now there's no chance of A happening. Oh, okay, so this is interesting. So there's no chance of them both happening together. So the probability of A and B equals 0. Okay. Well, we call these things mutually exclusive. They can't happen together. If one's happened, the other one can't. So these are mutually exclusive events. Okay. And you can probably see this quite easy on a diagram. On a diagram, a Venn diagram, so we have A and B. They've got no intersection. They don't overlap. Mess on there. So mutually exclusive events. Probability of A and B equals 0, and that works in all your formulas. And on the diagram, they don't intersect. Okay. So really here, if I explain two things for you, independent events and mutually exclusive events, you need to know which formulas relate to which situation. The diagram in this case, diagram in this case would be a normal diagram, it just depends how much they overlap. And you need to know how to use them. Okay. It might mention in an exam question each of these terms. Okay.
Right, so let's look at this final example. So we know that events A and B are independent, and that's going to be really important. We also know that probability of A is 1/3, probability of B is 1/5, and we're asked to find these various things. Now, as knowing that these two things are independent, that means that the probability of A given B is the same as the probability of A. So when we go to our multiplication rule, where we've got the probability of A given B times B, sorry, the probability of B is equal to the intersection, well, we know that this is just the probability of A. And so because they're independent, we know this is true. The probability of A times the probability of B is equal to the intersection. So to do part A, all we need to do is the probability of the intersection is equal to the probability of A times the probability of B, which in this case is 1/3 times 1/5, which we all know is 1/15. Right, what about part B then? Now at this stage, because we know the intersection and we know the probabilities for the two events, then let's draw a Venn diagram. So we do our box for the outside, we draw our two circles, and we start in the middle, where we know the intersection is 1/15. Now we know the probability of A is 1/3, but we've already used up 1/15. Well, we know that 1/3 minus 1/15 is the same as 5/15 minus 1/15, which is 4/15. So this must be 4/15. But we know the probability of B is 1/5, so we've got to do 1/5 minus 1/15 to get what's in this section. 1/5 is just 3/15. So that is actually 3/15 minus 1/15 is 2/15. So that goes there. Well, we know the whole thing must add up to 1. So at the moment we've got 7/15, so we've got to have 8/15 on the outside. Right, well now we're in a position to be able to answer this question. It's asking us what is the probability that we're in both A and not B. Well, this is where we use our shading. So let's shade A. That looks like that. And now let's shade not B, going the other way. And so if we look at which bit we want, where two shadings overlap, then we can see that we just want this bit here. So this is the intersection of A and not B. So the answer must be 4/15. The final bit, we want the probability of not A and not B. Well, this just stands for basically the outside, because we want to be not in A. Well, that's got to be this bit around here, but also not in B, which is this bit around here, and it's the outside that satisfies both. So that will be 8/15.
Okay, in the words of Wycliffe Jean, one time. Example 11, take a bazillion. Alright, example 2, still shapely done. It's like this is my Achilles heel. I normally think of this as my best topic. We roll on, keep trucking, and we roll on to example 11.
Yeah, are we rolling now?
Yeah.
Am I in shot here?
Yeah, I can see your cheek.